Hello everyone and welcome to this webinar with the title Audio Device Simulations for Virtual Prototyping and Algorithm Design. My name is Daniel Gert Nielsen and I'm the product manager of the Treble SDK, and I'm very happy to welcome you here from Treble HQ in downtown Reykjavik. We have a very packed agenda today, so I'll start out briefly with an introduction to what is DRTF from CAT and what kind of value does it bring to your development efforts. Then my colleague Sylvie will take a deep dive onto the feature with this feature spotlight, and then we're going to go over a few demos, a few examples of how to use the feature for virtual prototyping, and then also an example for how you can generate device-specific data for machine learning with this feature. And then finally, at the very end, we're gonna enlighten you a little bit on what lies ahead for this feature in the coming time. So let's get started. You are probably working in audio development, either as a hardware engineer, machine learning specialist, signal processing, traditional DSP, and so on. And you know that requires a lot of effort to make these cutting-edge products. You also probably know that data quality and realism is very important when you're working on the next generation of AI, DSP, and hardware. I would guess that often you rely on measurements and measurement campaigns to do these large data acquisitions to get the correct data and get the correct insights for these devices. But these measurement efforts are very resource heavy on a large scale. So that's why we have developed this feature to give much quicker insights on how your device performs in these complex acoustic environments, but also enabling large data acquisition efforts targeted towards machine learning with device-specific impulse responses. And we're very proud to have developed this feature in collaboration with some of our early customers. And these customers are some of the biggest companies in the audio tech industry. And we're very happy to have a mature feature now that we can share with everyone. So let me just quickly introduce what the feature is. It allows you to render in a device or a prototype into a simulation of, for example, a restaurant or a virtual laboratory and so on. So a very complex environment. But the game changer here is that you do not have to re-simulate every time you do an augmentation of your device. Meaning, for example, if I want to rotate my device around to get angle-dependent input, I can do that in post-processing, taking just a few seconds. Similarly, I can swap out my device in these complex environments. So if I want to do data acquisition for a smart speaker with 3 and 6 microphones, I can just render in the device in post-processing, and also in a few seconds I can get this device-specific output. There's no reason to re-simulate for me. Then that saves me a lot of time, but it also saves me a lot of cost. So that's quite a nice part of this feature. So being a post-processing feature, this enables very fast workflows. It's traceable, but it also enables you to do very rigorous testing of prototypes in complex environments, because you can get very detailed insights, because you can do more with the time that you have. It also enables you to get these device-specific data for your various devices. When you want to create this large data set for machine learning training, you can simply render in your devices into thousands and thousands of scenarios and get all the data you need for your training. So a bit about how this feature works. You have some static data that you simulated previously in the Treble SDK, for example, of a few of our living rooms or some test rooms that you go over in your company, or maybe a virtual lab, for example, an ISE room and so on. You have that static data simulated already in the SDK. And then we have previously enabled that you can import a measured device-related transfer function, or HRTF, into Treble, upload it into our library, and then use that to render devices into these simulations. The novelty now is that you can now just upload a CAD file into the SDK, specify your microphone locations on this device, do a pre-simulation, and then it will be added to this organization library, or your organization library, and then you can use it to do these device renders, changing out devices, rotating it, and so on, to get the device-specific data that you need. If we take a little bit of a deep dive into some of the, you could say, workflows that motivated this feature. A lot of people, I guess, in this webinar have the experience of developing audio devices, and you know that this measurement-based prototyping is quite time-consuming because you rely on a lot of external parties for you to succeed. So let's try to walk through it. You have a new design proposal arises from either your department or mechanics and so on, but then you need to go to the tool shop to get this prototype manufactured, so 3D printing or traditional manufacturing methods. Then you have to find microphone components, speaker components. You have to attach them, you have to solder them, and you have to get a test board. You have to do all this setup. And then finally you can go to the lab. You can set up the measurements, so all your sources needs to be set in the correct positions. All your reference microphones needs to work and be correct place. And also all your device microphones needs to be working accurately. And all this takes a very long time and relies on tool shops, vendors, other people essentially. And then finally you can get to a point where you can verify and test your acoustic hardware, how does the frequency response look and so on in this IC room, for example. And then you can also verify and test your algorithms. And then at the end you will either approve or reject your design. So if you reject it, maybe there was a problem with the measurements, well, then you have to go back to the lab, set up the measurements again, redo them and so on, taking probably a few days. If there's a problem with the prototype, then you have to go all the way back here and then manufacture it again, resolder, re-glue the microphones and so on, and then do the measurements. Also a time-consuming process. And then in the end, if it does not perform, it's back to the drawing board and work on a new design proposal, essentially. We see a lot of great advantages with this simulation-based virtual prototyping. Again, you start from the same initial step. There's a design proposal. That design proposal comes with a CAD file. You can upload that CAD file into Treble, quickly put on the microphones with just a few commands with the coordinates, and then you have already pre-run this virtual lab or whatever environment you would like to test it in. It just takes a few seconds to then render in these devices and get the device-specific impulse responses. And then you can quickly verify and test the acoustic hardware, but also you could run, you can say these some speech samples through and then verify and test the algorithms. This process takes minutes or hours, and you as the engineers in control, not relying on outside stakeholders making this process for you very fast. And then at the end, of course, you can approve the design or you can reject it. If you need more data, it's quite fast for you to render again the device. So maybe you want a few more head directions if it's a head one device, or you want to rotate the device slightly, and so on. You can very quickly augment the data and get more. Don't need to go to the lab. If you need to augment the prototype, say that you need to add 1 or 2 extra microphones to test something, then you can quickly do that with adding a few more coordinates and then run the short anechoic simulation again and then render in the device and the environment, taking you a few minutes essentially. If the design is not performing, well, in this case, it's also back to the drawing board and you need to come up with a new design proposal. But the timeline here is generally measured in minutes and not in weeks or months. The feature can also be used, as I alluded to a little bit earlier, for device-specific data for machine learning. So for some applications, it's quite beneficial to have the device when you build your dataset, and that can be done, for example, with measurements. But large-scale data acquisitions is very resource-heavy for these device-specific applications. I have a short animation here showing just kind of moving some furniture around to augment the acoustics of a room, absorbers, moving the device around and so on. We're talking weeks or months even. You know that the device geometry, it introduces phase delay, it introduces diffraction, amplitude changes and so on. So there is augmentation to the impulse response that is quite neat to have as a part of your training data, because that will allow your machine learning algorithms to optimally exploit these array-specific designs. It can also improve a lot of different algorithms. I've named a few here, taking a spin on you can say the spatial aware algorithms that run on a lot of different products these days. So that could be source localization, source separation, distance estimation, and room estimation. All benefit greatly from having these device-specific impulse responses generated, which you can do very fast with this new feature. So just summing up here at the end, you can, with this feature, go from a CAD file to comprehensive acoustic performance in minutes or hours instead of weeks or months. You can identify and fix design flaws before you build expensive prototypes. Usually for development workflows, you have a fixed time that you have to test ideas. You can say, this feature will allow you to do more with that time. You can test maybe up 10 designs instead of 1 or 2, essentially using your time to be creative and test more hypotheses. And you can also create these early audio demos for your customers, your engineers, decision makers, and key stakeholders, so you can bring in more people early in the process and make these key decisions together, and that will reduce the overall risk of these large development programs. You can improve your audio machine learning algorithms by utilizing these device-specific data, and you can very fast generate multiple data sets. So you imagine that you have generated thousands and thousands of rooms, and you want to then test if microphone configuration A performs better than microphone configuration B. Well, with this feature, you can just render in the 2 configurations across the datasets, ensuring that they're in the same position, with the same orientation and so on, and then the only variable in this dataset generation will be your microphone setup on the devices, allowing you to then take a enlightened decision on how to proceed with your microphone array for certain machine learning applications. So that was a quick intro, and I'm very happy now to give it over to my colleague Sylvie to take a deep dive on this feature and show you some of the more technical details of how it works.
Thank you, Daniel. I'm Sölvi, and I'm gonna give you an introduction to what we call device-related transfer functions, or in short, DRTF, which now, from this day, you can simulate in Treble. And the reason you want to use a DRTF, as Daniel briefly mentioned, is, for example, you make a simulation. It can be expensive, take some time, and then afterwards you realize, oh, maybe I don't want this person in the simulation to have glasses. I would rather that that person has headphones. And then you can, basically without rerunning a simulation, you can switch out the device in the simulation. And we've done this study in a fully furnished room where we did measurements. You can see the rendering of the room on the left here, and we placed this KEMAR mannequin into the room. We then ran a simulation where there was no KEMAR inside the room, and then in post-processing added the KEMAR with like binaural microphones into the simulation in post-processing using a DRTF. And here you can see how nicely this worked, that in blue you have simulation data, and in orange you have the measurements for the right and left ear. And you can see here the frequency response as well, and you can see that these add up really nicely. And I want to give you a brief introduction to how we treat these DRTFs inside our simulations. So we have these 2 things. We have what we will call the room response, so what happens inside the room that we want to simulate, and that's what happens inside the simulation. This can be a wave simulation, it can be a hybrid simulation. And then at a spatial receiver location, and around that location, we do some array processing to kind of capture the effects of the room around that location. And then while we do that, we keep our DRTF or transfer function kind of on the side. We then take this array processing results and project it onto an orthonormal ambisonics basis, and we do the same for the DRTF. And then in post, you have the effect of the room, you have the effect of the device. You can rotate the device any way you want, and then add them together. And at the end, you come out with this rendered signal, which would be the same as if you would have included the device in the simulation from the beginning. And the nice thing about this is that now in geometrical acoustic simulations, it would have been hard to include the device from the beginning. But this way you can actually include it in both geometrical and wave-based simulations, and you don't need to rerun a simulation to switch out the device or rotate it or whatever you want. And now, from today, you can create the DRTF in Treble. You've always been able to import the DRTF using measurements, but now you can do it with simulations. So in order to create the DRTF, the information we need is the response at the microphone location or the device location from different angles, and ideally from hundreds of different angles. So in a simulation setup, theoretically we would need to do individual source simulations from hundreds of different angles, which would become very expensive because these are many simulations. But thankfully in wave physics we have a thing called reciprocity, which means that this scenario that we have in this illustration is equivalent to this one here, where we're listening at hundreds of different angles and we only play the sound source from the intended microphone locations. So this is what we do in the simulation. We do a simulation from the center, from the actual microphones on the device, and listen at a sphere around the device. Then we take these results and we encode this into ambisonics, as I mentioned before, to get this on like an orthonormal basis that we can then put into the effects of the simulation, of the room simulation that we had before. And we have different ambisonics orders. We offer up to order 32 in ambisonics, and I want to briefly show like why ambisonics order matters. And for that, I have this little example where I have two plane waves propagating in perpendicularly at 1 kilohertz frequency, and we can combine them into this nice little checkerboard we have here. And then what I'm going to do is I'm going to place an ambisonics receiver in the middle of this field and try to reconstruct the field for different ambisonics orders. We'll start here at ambisonics order 4, where we managed to resolve the wave field quite decently at the center, but as we go further away, our solution is quite bad. But if we increase the order, go up to order 8, now we can see that the area is getting a lot bigger, and up to 16 we almost resolve the entire wave field that we have here. And this was a sphere of 1 by 1. But on the other hand, we also have the frequency dependency. And if we now increase the frequency of the wave field up to 2 kilohertz and keep the ambisonics order fixed, now we resolve a smaller area. So it's a balance between what frequency you want to resolve, how big your device is, things like this, which helps you decide what kind of ambisonics order you need for your DRTF. We have all sorts of tools in the SDK which help you decide on these things, and I'll show this later. So if we now look at this fictional device here, what you would have to keep in mind if you want to create a device for something like this is that ideally you want to be able to resolve the wave field kind of around the device in a sphere that encloses the device. It doesn't have to be bigger than the device, like in this case, but it has to, ideally, if you want to capture the full effect, it needs to be around the entire device. This device has a length L, and this is sort of the rule of thumb formula that you can use to decide on which ambisonics order you use for which frequency you want to resolve. So N here is ambisonics order, speed of sound, and then we have frequency here. But it's not only this that the ambisonics order does for you, it's also that with a higher ambisonics order you can capture a more complex pattern. So here for the same microphone with different ambisonics orders, you kind of capture a different level of complexity of the response of the microphone. And I have an example here, which is not for this device, it's for a KEMAR, where we render the ear, one of the ears, with on one hand ambisonics order 4, and on the other hand ambisonics order 16. And you can see that the ambisonics order 4 is kind of like low pass filtering spatially compared to the ambisonics order 16, where you capture much more detail. So now we're in the SDK, and in this demo I'll show you some tools that we have to estimate the required ambisonance order for your device, and I'll show you a simple interface of how to set up a device creation simulation, which will also have an intensive guide on the documentation website upon release. And then lastly, I'll show you how you can then at the end analyze the results of your device and how the device you can expect it to perform. We start by initializing the SDK and making a project, and then now, like basically from this picture that we had in the slides, we can. I have a tool here where you can plot the ambisonance order, what you can expect to resolve from the ambisonance order. And here what we have is on the x-axis we have the maximum frequency that you can expect to resolve, and on the y-axis we have the radius of the enclosing sphere of the entire device. And for example, for order 8 you can expect here at 6000 Hertz that you can resolve a sphere of radius about 7 centimeters. But if we go up to order 16, you can see that it goes higher, and up to order 32 we can expect at 6K to be able to resolve a sphere of almost 30 centimeters. And this is something that you can use beforehand to kind of estimate what you want, and it's using the rule of thumb formula I mentioned in the beginning. Another tool which is it's the same but presenting the information slightly differently. Here you can print the guideline table for if you know the radius of your device, and then the ambisonance order that you expect to use. You can print the table like this, which tells you that for whatever ambisonance order you can expect to resolve this frequency. And for this demo I'm going to be using a device that has an enclosing sphere of a radius of about 20 centimeters. So it looks like we're going to have to use 32nd order to properly capture the device. And here I'll show you how to set up a simulation for something like this. And all you need to do is to have a file that you with your CAD file, and you could add this to the SDK. I already did it, so I'm gonna just get the model by the name, and I'll plot the geometry. This is how the device looks. It's kind of a simplistic device, and I'll place microphones here to the two sides, the right and left, here one slightly to the back and one at the front. And this is what I define here with these device microphone placements. I define these 4 points. I define the frequency of my free field simulation and the ambisonance order that I want, and then use this to set up a simulation. I've already done this, so I'm not going to do it now. And then what you have to do once this is done, it can take up to like 2 minutes usually, and then you can add the simulation to your project and start it. And you just wait for it to finish. But I already did, so I'll just get the simulation and plot it. It takes a few seconds to get the simulation and put up the plots, and we have it here. In the meantime, I'll keep this thing running. So here I have the simulation. You can see the sphere that we have, and all those dots here, those are receivers. And inside here we have the device. See, we have a microphone here at the front, one at the center, slightly further back, and then 2 to the sides. So when we have the results of the simulation, we can use those to create the DRTF. And afterwards we add the device to the library, which then does the ambisonics fitting. And when you create the device, you can pick the ambisonance order. It has to be equal or lower to the one you used when you made the simulation. And what I've already done is I've created the same device for order 32, 16, and 8. And I have those here. And then I'm going to show you a little plotting tool that we have to analyze the results. So here what we can do is we're plotting the transfer functions of the different microphones based on the spherical harmonics or ambisonics. So here we can look at transfer functions for the different microphones that we have, and we can look at different angles and see how the response of the microphones changes. Then we can also go back to and see the spherical harmonics fit. What you can see here is how the energy is distributed in frequency on the x-axis and in ambisonance order on the y-axis. And here on the top left and top right microphones, we can see kind of how most of the energy is along this line here. It's much deeper than the one for the top center microphone, and that's because the top center microphone is very close to the origin. And then we need like lower ambisonance order to render higher frequencies. And then what we also see this kind of faint area here, which relates to the size of the device and the effect of the actual device, like diffraction around the edges and things like this. And we can see that for the top left and top right microphones, we definitely have some energy coming up to order like 25, 26, but less. But most of the energy is close to order 16. What we can also do is plot this polar pattern. So here we're plotting from above, and we're plotting then as we go around the axis with, as we go around this axis, we plot the response of the microphones. And we can see here how the microphones on the top right and top left, they're basically symmetric in that plane. And we can add here the microphone at the front, where you can see how it's very sensitive when the wave is coming from the front, but less so when it's coming from the back, which makes sense. But to analyze how nicely you manage to fit the input transfer functions, you can click this check mark here to compare to the input, and you can see here for this particular one with 32nd order rendering, the fit is basically perfect up to the entire frequency range. And then what we can do is check on the other devices, because I made for lower ambisonance orders, like for order 16, where we capture most of the energy, but probably not all of it. Can plot this again. Here we see the spherical harmonics that they are kind of, we're obviously not getting all the energy because it kind of stops here. And if we plot the transfer functions and compare to the input, you see for some angles it's happening, it's working pretty well, but for some of them definitely less so. See here it's diverging quite a bit, and especially for angles coming from below. If we look at the front microphone, it's quite off, but very good for the lower frequencies. And then like we can continue this story, go even further, and do the compare to input again for this one. Again here it's quite obvious that we're cutting off a lot of the energy. Then if we compare to the input, we're already off quite a bit. We're not catching this dip here at all, for example. And so this kind of demonstrates the effect that it has to properly resolve the whole sphere using very high order ambisonics, like the 32nd order ambisonics. But at the same time, it also shows you that, like, if you're more interested in the lower frequencies, then the other thing can be okay. So that's it for me. Thank you.
Welcome to the first of the use case demos for the DRTF from CAD feature. This demo is all about showing you how you can use the feature in a virtual lab setting. So imagine that you have some hardware design that you want to test and extract some parameters from, either for objective evaluation or some algorithm testing with involving these IRs with speech. So in this case, it's some smart glasses that's mounted on a mannequin. So we can quickly load in the smart glasses into the SDK and define some microphone positions here. Then I'm just computing what ambisonics order I need. Sylvie also talked a little bit about that in his last presentation. And for importing a whole mannequin into the SDK, we need 32nd order ambisonics to resolve that correctly. The next thing I'm doing is that I'm setting up this free field simulation for the DRTF generation. So what this does is that it takes your device in, and then it creates this anechoic sphere around it automatically, so it knows the size of your device and then scales accordingly. But then it also crucially automatically generates all these receivers around the device that is needed for this very high ambisonics order encoding. We're doing device simulations, and it's quite a detailed device. So before it's loaded into the SDK, we did a combination of a CAD file with the smart glasses and the mannequin. So that's done outside of the SDK essentially. And here we have some very, very fine details, which means that the mesh is also fine. Typically, that's a pretty big bottleneck when you're doing very large room simulations, because your computational time depends on the smallest element in your simulation. And they will be very small for these type of devices. But by pre-computing the device, we actually run the simulation before, and then you can say we include the device in the room with this post-processing step, meaning that your small elements actually doesn't affect your runtime. So we've set up the free field simulation in an automatic way, and down here we can plot it and take a look at it. So what this function or method does is essentially it places the mannequin with smart glasses automatically in the center, and then populates this anechoic sphere with the receivers around it. And here we want to then compute this transfer function from these 3 microphone positions on the glasses with, you could say, very fine geometry details and so on for this room simulation. So the next step would be to run the simulation. I've already done that. It takes 20 minutes, maybe a bit more, up to 12 kilohertz, but we only need to do that once. And then I would, after that, I would then add the device to this library, and then you have that for all eternity and can render into post-processing again and again if you want to. So the next thing I'm doing is that I'm uploading a virtual lab to the SDK, and let's just see how that looks here. So it's a nice rectangular room with some absorbers on it. Could resemble something like a IC room or listening room or something like that. Good for testing devices in, essentially. I will then apply materials to the walls, so I get the correct boundary conditions, concrete, wood, and some absorbers that we have measured in an impedance tube. And the next thing here is that I then want to define my receivers and sources in this lab setup. So I find the room center in this case, and then I create a spatial receiver with 32nd order ambisonics, and then I place 3 loudspeakers around it to create this nice test scenario. I will then create a simulation definition, and here we're running a 4K hybrid simulation, meaning that the DG solver runs up to 4 kilohertz, and then the GA runs from 4 kilohertz to 12 kilohertz. In the lab here, we can see that we have the spatial receiver here in the center. Let me just hide the ceiling here, so it's a bit easier to see. The spatial receiver is in the center, so that's where we'll render in the mannequin. And then we have these loudspeakers placed around it. The coordinate definition is such that if azimuth is 0, then the mannequin is facing towards this loudspeaker here. So if I did not already have a simulation of this lab, I could then simulate it, but we use this lab quite often, so instead I can just fetch the lab simulation that I have previously run and load it into our results object, and then I can continue to work with the results object and then render in these glasses in the spatial receiver location. So I choose here azimuth rotation of 5 degrees, so meaning that the head is slightly turned. And then I will basically, what this function now does is that it will create these device-specific impulse responses from the source, the 3 source locations to the 3 receiver locations, giving me these device-specific impulse responses that I can then continue to work with. And the next thing I will do here is just do a quick comparison plot. So this is like an objective view on the free sources to the microphones. So we can, for example, just inspect the frequency response, or here the impulse response of microphone 1 for the free sources. It's quite straightforward to look at these and then compare the results essentially. And then I can revisit this if I choose to then turn the head of the mannequin again. We also have built-in functions in the SDK to render speech. So I load in some anechoic speech examples here and some noise, and then I can create an audio scene so that would correspond to, you could say, a lab scenario where you played speech over from the free sources and then record it on the device. That's essentially the exact same exercise we're doing here. And I can then feed this, you can say, then you get the audio signal on all three microphones, and then you can feed that to your algorithms and see how they perform, or you can simply listen back to the raw sound of the room through the device microphones. So that will sound something like this.
Ef við skoðum dýrsfrumu, þá hefur hún hin ýmsu frumulíffæri. Ysta lagið, það frumuhimna. Hún úr fosfólípíðlagi ásamt prótínum.
So, for example, that's sort of the workflow, and then it's quite straightforward for me. So if I want to get more angles, I could either create a for loop around this rendering step, or I can simply just, if I want just a different angle, for example 15 degrees, so again slightly turning the head a bit more, I can just run this again. It will take these around 30 seconds, and then you get the device specific impulse responses for the free sources to the free microphones on the device for this new orientation. So that's about sums it up for how you could use this feature in a virtual lab scenario. I hope you can see some interesting use cases for your product development efforts and see how this can help you speed up your development cycles and test more products in a more resource lean, or you can say resource not so resource heavy way essentially. All right, now for the second demo of the virtual prototyping capabilities of this DRTF from CAD feature, we're going to look at a more realistic example. So we're going to dive into a restaurant example where a hearing aid user will try to listen in on a conversation with a talker right in front of the hearing aid user. In the scene, there will be a lot of noise coming from various different sources. So we're just gonna load in the restaurant here in the SDK. This is actually from our model library. I believe we have close to 1,000 restaurants there, and all the purple dots here are these suggested positions where you can place sources and receivers to sort of conveniently have realistic placements of those. You are of course also free to place them wherever you like. But we are going to work with this metadata in this notebook and use these positions to place both the multiple sources in the room and also the spatial receiver, where we will then render in this mannequin wearing a hearing aid. So we'll just go ahead and apply the materials to the restaurant example here. And we load in different material categories, and then we do a random material assignment, but adhering to the fact that we want a maximum say-by and reverb time between 0.4 and 0.5. Just gonna go ahead and run this code, and then it assigns some different materials to the different layers in the model. And then we will use the source. Then now we will define the source and receiver positions, where we're using this metadata from the room database that I just showed you before. So that is that, very fast. And now we're going to create the simulation definition, essentially setting up this hybrid simulation with a crossover frequency of 3000 Hertz. Can look now here at how, I just minimize this, get a bigger view here. So what we have here is that we have a spatial receiver position here at 0, which is where the hearing aid mannequin will be rendered in, and right across the table we have a directive source. In this instance we use speech directivity, so we can render in some talk or audio here essentially to create an active listening scenario for the hearing aid user, where the selective hear-through algorithm has to focus on the person in front of them and try to pick up the sound. but then we have 5 different noise sources scattered around the room, where we can then convolve different noise sources in to make this a very difficult environment for the hearing aid to operate in. So we could go ahead and run the simulation. I've already pre-run it, so no reason to do that. Instead, we can download the specific simulation results here. And just for you to sort of see what kind of hearing aid we're working with and how this import could look like, I'm here loading in the previous run simulation from this project. This has been run up to 12K essentially. So here we see this anechoic sphere with all the receivers around it, so a lot of receivers because it was run up to 32nd order ambisonics. And then we see this behind the ear hearing aid here of the mannequin with two microphones on it. So we can go ahead and load this into the simulation. What essentially is going on here is that we'll fetch the hearing aid from the device library. Then we will specify a azimuth rotation of it. Here it's 0 degrees, which means that it's facing the in positive x-axis. So we have the coordinate system down here on the right. So we see that the hearing aid user will be facing directly towards the talker here. And then what we're rendering now is the you can say the device-specific impulse responses from all the source locations to the device, so we get the device-specific output in all cases. Okay, so now we've rendered in the device-specific impulse responses. Then in this example, I want to convolve some audio in to generate this complex audio scene for testing the hearing aid. So we'll load in some anechoic speech, some different noise sources, and so on. And then I can listen to the total summed playback. Yeah.
Ef við skoðum dýrsfrumu, þá hefur hún hin ýmsu frumulíffæri. Ysta lagið, það frumuhimna. Hún úr fosfórlítið lagið ásamt prótínum.
So coffee machines, there's a birthday party going on, people are clapping and so on. It is, and then you can say the task for the hearing aid is then to pick out the speech from this Icelandic woman sitting across the table. We can also, we can also look at objective metrics such as SNR and SNRI. So we did a short calculation here to show how this data can also be used for that. So you can compute the SNR for a single microphone with this data. But then you can also see if you then add a second microphone here. So first was for the front mic only, and now we compute the SNR for front plus the back microphone, and then we see it improves. So you can both use this to evaluate with speech data, but you can also dive in and use these more objective metrics. You could of course also plot and extract impulse responses, frequency responses, EDC curves, phase response, and all these kind of things. So that's the example for the hearing aid. Now moving on to machine learning data generation. The last demo of the day is about creating synthetic data for machine learning training, and we'll do that by using this DRTF from CAD feature, where we will, across hundreds of rooms, render device-specific impulse responses across multiple devices. So let's get started. Just logging into the SDK here, fetching the correct project, and then I just wanted to briefly mention that we are working with an existing dataset. That's one of the powerful things about this new feature, is that you don't have to resimulate, right? So here we have an existing dataset that we have created with the varying source and receiver configurations, also different source directivities. We looked at different room volumes, different room shapes, but also randomized the absorption, so you have different absorption on different walls. And finally, we added also scattering objects into these randomly generated rooms. This was done in a previous webinar in February, and you can actually find the use case on our website, docs.treble.tech, where this use case is available for download, and you can try it out with the SDK. But in this example, this has already been run, and we essentially just need to set up our devices that we want to test and then use this dataset. So here I'm using a cylindrical device. It could be a speakerphone or a smart speaker. I have an example where we have 4 microphones on top and another one where we have 6. And this is a quite typical workflow where we are a little bit unsure in the R&D process, how should our microphone array look like and how many microphones should be in it. And here we basically enable a fast testing and of that hypothesis, so you can figure out what works best. So you could create 2 data sets, one with 4 microphones and one with 6, and then you can train your algorithms and test what the performance is, essentially. So if we just quickly look at how these devices look to get a feel for that, we have this cylindrical device with 4 microphones here, placed on the top surface. So again, we have this free field simulation with this time 16th order ambisonic, because the device is much smaller than the mannequin we had before. And then similarly for the 6 microphone case, we have that here, where we just added essentially 2 additional microphones to the design. Then I would add it to the project, and essentially later on I will then start the simulation. But before we get to that, I just wanted to show you how you can visualize the mesh in the SDK. So working with these devices can often mean that you will have very fine details in the model, and then it's a good idea to inspect how the mesh looks, the computational mesh looks for your device. And here we have the 4 microphone device, and we see that the device shape is very well preserved, and we don't have any tiny elements. The same thing can be said for the 6 microphone case. We can also look at the mesh efficiency percentage over here, where higher numbers are generally good. We can see that the device geometry is nicely preserved, and we have nice looking elements. We can then run the simulation and get out the data so we can create the device. This has already been done, so I'm not going to do that again. And then this step essentially creates the device and then adds it to the library. Since this has already been done, I can go ahead and fetch my completed dataset simulation. So here we see 300 rooms constituting 20,000 room impulse responses to these spatial receivers. I can pick out a random shoebox and a random living room just to visualize how this actually looks like. So a shoebox room could look something like this, where we have randomly placed sources and spatial receivers, and then some objects in the room to add some scattering, so it's not just a regular shoebox room. And then we have a living room that essentially draws a room from our model database, which is quite nicely populated with different furniture and so on. We see the spatial receiver location here in typical placement scenarios, and the sources likewise, essentially. We can then go ahead and, as an example here, just render in the 4 mic device and the 6 microphone device into these rooms, and then we can plot the impulse response and the frequency response for one of the cases, just to give you a feel for how that looks like. And then afterwards we can then do it on the entire data set, essentially. So we rendered in the 2 devices in the living room and in the shoebox room. So we can just take a look at the device with 6 microphones. If you want to inspect maybe a single room before we start out, we can look at the impulse response and frequency response and so on. And we can do the same thing for the living room if we want to verify something. But here's what it's all about, is to then render in the devices into this large data set. I mean, this has been quite a short demo, but that also kind of highlights how easy it is. We have already pre-run all the simulations, the bulk of the work. The only thing we need to do is essentially define a new device with a new device microphone configuration and so on that we want to test and generate data for, so we can train algorithms and evaluate performance on new devices. So essentially that's what we do here at the end. We download the results of the simulations, and then we start the rendering of the devices into this large data set. And this is going to take a little while. We have 20,000 IRs, of course, so I'm not gonna let it run to the finish line, but I hope that this gave you good insights into how this can bring value to your machine learning efforts and start to include your devices in your machine learning training. The webinar is coming to an end. We hope you liked it. We hope you liked the feature and what workflows it enables. Draw some inspiration from the examples. We'll also be happy to share those with you after the webinar. This last section is just to show you what lies ahead for this feature. And the first thing we're going to enable in the very near future is batch processing, meaning that you can run as many device renders in parallel as you have concurrency. We're working on some import improvements to CAD simplifications to make that workflow even simpler than it is today. We have made quite big strides here, but are continuously working to improve in this area. So that will also be coming later this year. We will enable STL file import. We recognize that this is one of the formats that's quite often used in, you could say, native CAD softwares used for device creation, and then we'll look towards if we should enable even more formats in this space. And finally, we are working quite hard on making re-renderable devices that are close to walls or tables. So that could be a speakerphone on the table or a soundbar on a wall. These are notoriously hard to make re-renderable because the near-field acoustics are quite complex. But that will also come later this year or start of the next year. And now we'll jump into Q&A. We look very much forward to answer your questions there. Hello everyone. Before we start the Q&A session, I just want to mention that this feature will go out on Monday, so that you will be able to test it in the SDK. On Monday we will also release the notebooks that we just showed you here in this webinar. And now we will dive into the questions. So if you look below the webinar screen, you can ask questions in the chat, and then we'll go through them and answer them. And the first question here is from an anonymous person. Can you account for the impact of adding risers into a room for seating and changing the room building materials? And I'm not entirely sure what you mean with risers, but I can say that you can indeed change the room geometry in the SDK. And you can also play around with the materials on the walls and so on to change the boundary conditions and change the room geometry. The next question is there a limit on the size of the virtual device that you can swap out? And maybe you can take that, Sylvie.
Yeah, so this kind of nicely alludes to what I was talking about with respect to the ambisonus order. So for larger ambisonus orders, you can have larger devices, but there's of course always some sort of limitation, especially at high frequencies. Then you can't really swap out some really big devices. There's like a limit of a few tens of centimeters in radius, I would say, for the very high frequencies and higher ambisonus orders. But if you're more interested in the low frequencies, then the size of the device that you want to swap out increases. So I would say a yes and a no.
And the next question is, if the ambisonics order needed is larger than the one currently supported, 32, do we need to use multiple ambisonics receivers, for example, per microphone position? And maybe that would also be good if you could address that.
Yeah, so I would say that approach would not really yield the results that you would like, I think, because there are effects of the actual size of the device and things like this, and if that can't be supported with the 30-second order, probably won't be able to support it with two 30-second orders, because both of them are kind of related to each other and they have an effect on each other. So I don't think this would be, I mean, there may be cases where this works, but it definitely doesn't work for all cases. But feel free to submit some sort of feature requests on supporting an even higher order ambisonics, because that might be an option.
Indeed. Can Treble simulate speaker outputs from devices or only microphone inputs? As we also showed briefly in this virtual lab demo, then you can indeed also model complex devices such as loudspeakers and so on in the SDK. So you can also assign a source basically and model a device that radiates into a room. You can say the difference here is that for these source type devices, you cannot re-render them. You basically have to run a new simulation. And then Louis asked a question. Great presentation. Thank you very much, Louis. Are the slides available, or is there a link to the video for those who attended the webinar? And there is. We will send out a recording of the webinar later today, and we'll definitely also be up for sharing more material with you. You can reach out to contact@treble.tech and be in touch, and we'll be happy to provide you with additional materials. Of course, the notebooks also goes out on Monday, so you will have those as well. Next question. Sorry, I missed the point of source modeling. Is it only its geometric diffraction that is taken into account, or also sound radiation from active elements? Maybe that's a question for you, Sylvie.
So to some extent, like, we do take into account the geometric diffraction, and it kind of comes from the wave-based nature of the simulation. And at the same time, like, the radiation from the active elements, the effect of the location of the active elements is taken into account. It just kind of comes implicitly from the simulation. But we're not assigning any specific directivities to the actual radiation. We are only basically taking into account the location of the microphone where it's located at the device.
And then Torius asked a question. I hope I pronounce your name correctly. Are you able to assign materials to the device? Currently, when you set up this device creation, we assign the materials for you, so it's done in an automatic way. And here we basically assume that the material is completely reflective. So currently, it's not possible to assign custom materials to devices, but we're happy to take a feature request on this and implement it at a later stage. Could you give some examples on virtual tests that would be ideal to run in a virtual lab setup in the Treble SDK? I can also take that one, so thank you for that question. For example, tests where you have these repetitions, so you can say sound from many directions. So for example, if you have a mannequin on a rotating platform where you need impulse responses for every 2 degrees, well, here you could set up a for loop in the SDK and just loop over the angles and then render the devices for each and every angle. Similarly, if you want to test, let's say, 5, 10, or 20 different device configurations, you can also in the same room render in these different devices and then do a direct comparison between them. And finally, you could also do some quite nice listening tests in a virtual lab. So if you had a listening room, you model in the SDK, and then you could listen to your device before you manufacture it and sort of see if it sounds as you would expect, basically. And Christian asked a question here. Can both sound sources and microphones automate and move in the space during simulation while also plotting frequency responses for analysis? I don't know, Sylvie, could you try to address that one?
I don't know exactly what you mean with this, Christian, sorry. We can definitely not move sources around like during a simulation, like sources are fixed. In post, however, we can move microphones around, rotate, and you can also, of course, place more than one microphone in the room, and then we kind of estimate a moving microphone, while also plotting frequency responses for another. You can definitely plot frequency responses for all of our results for analysis. I hope that answers the question. I don't know if you have anything to add, Daniel.
Yeah, otherwise, Christian, please feel free to reach out to us on contact@treble.tech, support@treble.tech, and we'll be happy to take a detailed question and elaborate further if you feel that is needed. So Stephen asks a question here. You showed a very nice automatic setup of the DRTF simulation. Is it possible to have more custom control when setting up the short anechoic simulation? Maybe that's a question for you, Sylvie.
Yeah, that's definitely possible. The automatic way is wrapping a lot of more complicated functionalities, which we wanted to make it easy to run such a simulation. But if you need more custom control, there are definitely ways to do this, and this is something that we will go into in our documentation. It will be live on Monday. You can constrain some mesh-related parameters, impulse response length, size of the sphere, size of the receiver sphere. So there are a few tunable parameters for sure that you can play around with, but we also have this interface to do this kind of automatically, which tries to do it in a somewhat optimal manner.
Is there a limit to the amount of microphones that you can have on a device? Could I do 10 microphones, for example?
Well, yes, absolutely. You can do. There isn't really a limit. The only limitation, it's not a limitation, it's just that you need to do a simulation for every microphone, so it just becomes slightly more expensive, but definitely you can have as many microphones as you want.
Then Anonymous writes, thank you, and I just want to say thank you too for tuning in. We really appreciate it. And then last question here. So if you want, from Frank, if you have another question, then please shoot in now, but otherwise this is the last one. Frank asks, are there ways to compensate for the lack of influence of the source or receiver object has on the simulation? For example, a torso in a small room. Do you have a?
So I mean, so I guess you mean from that having the thing, it affects the wave field or the rest of the thing, not only at the receiver location. I suppose that's what he means. I don't have a quick answer for you on this one, but we do get the influence of the device on the actual recording, but I would have to look more in detail about the influence of the thing on the whole wave field.
And then finally, Anonymous asks, if the mix that I want to simulate are placed on an enclosure that is much bigger, is the order dependent on the max mic aperture or the size of the enclosure? And maybe that's also a question for you, Sylvie.
Yeah, this kind of depends a little bit on what you really want. If you want to capture the absolute full effect of the enclosure, that needs to be a part of the ambisonics. But sometimes the enclosure has an effect at the lower frequency than at the highest, at the highest frequencies. And then, for example, we've used this KEMAR thing, where at the highest frequencies the ambisonics order is capturing the head, but we're not necessarily capturing the full torso, but it still works pretty well because the torso has a more elaborate effect at the lower frequencies. So it kind of depends on what you want and what kind of enclosure it actually is.
And that was the last question of this webinar. Thank you so much for tuning in and listening to what we had to say, and also thank you for all the great questions. We really appreciate that. Feel free to reach out if you come up with more. We'll be happy to answer them.